Greetings all. Today, I'd like to talk about the impulse momentum theorem. We're going to discuss how force and impulse are related. We're going to describe the impulse momentum theorem. And then finally, we're going to use the impulse momentum theorem to solve some problems involving stopping distances, stopping times, how fast you can stop an object with a certain force. Let's talk first, though, about why this is important. I want you to consider car crashes. You're going to notice in momentum, we talk a lot about collisions, objects colliding together in some type of a change of momentum happening. Let's think about why cars have all these safety features they have now. Airbags, seatbelts. Why do these things help us in a car crash? Because initially you might think they wouldn't actually help at all. Consider this. If you're thinking about a car crash, you have a lot of momentum to start off with. So at the start of a car crash, before you've actually crashed there, you have a velocity that is large and the mass is the same. When you end your car crash, you have a velocity that is 0 and your mass is still the same as it was before. And so there's a change in momentum. You could calculate it by just knowing that, well, change in momentum, that's my impulse, and that's the final minus the initial. So it'd be m times v final minus m v initial. Now, it doesn't matter whether you're wearing a seatbelt or not, an airbag or not. Your final velocity is always 0, and your initial velocity is always really large. So your impulse, whether you're wearing an airbag or not, or a seatbelt or not, or have an airbag in your car, is the same. So why do these things help us? Well, it has to do with force. It's the force on you in a car crash that actually does the damage. And how can force possibly be related to this? Well, it changes, what changes the force is the amount of time it takes for you to crash. What an airbag does is it actually increases the amount of time you have. And that's what we're going to see really affects how much damage happens to you in a car crash there. So what you want to know is that impulse can be imparted to an object by applying a force over a time. The equation we can use for this is that impulse is going to be equal to F net times the time. Graphically, what that is actually is that impulse is the area under the curve of a force time graph. This is why seatbelts and airbags are so helpful. They increase that amount of time that you take so that even though you have a large impulse, that force is going to be spread out and doesn't all happen to you at once. This would not be a good impact for you because you notice that force goes up to a large amount there. But we can still figure out, well, what's the impulse for this graph? It's the area under the curve there, right? So if I go ahead and kind of shade in that area, the shape that it makes is a triangle. Well, to find the area of a triangle, it's just 1/2 base times height. Plugging in our numbers, 1/2, my base here looks to be about 40 seconds. My height looks to go up to 100 newtons. So in this particular case, 1/2 base times height, I end up getting about, looks like 2,000 Newton seconds as my area, which is also the same as my change of momentum or impulse. Now, this is a new unit we've seen before. Normally we thought about impulse as a kilogram meter per second. Here we're seeing a Newton second. What you want to know is that those are exactly the same thing. So you can say that momentum and impulse, momentum again, don't forget the symbol for momentum is P. In this unit we seem to use really weird letters for our variables. And impulse, which is represented by J, can be measured in kilogram meters per second, or they can be measured in Newton seconds. They're equivalent units. Either one of those will work. Let's take a look at how this might impact something. What I want us to consider in this example here is a 1.1 kilogram egg. And we're going to go ahead and say we're dropping it, it's moving at some velocity, and we're going to bring it to rest really, really quickly. So I have my 0.1 kilogram egg moving at 20 meters per second. I want to know what is the force required to stop this egg. So our mass here is 0.1 kilograms. Our initial velocity is 20 meters per second. If it's brought to rest, the final velocity is going to be 0 meters per second, and that time is going to be 1 seconds. 1 second. And I want to know the force. Well, our new equation we just found for impulse is force times time. I know the time. I'm looking for the force. but I don't know the impulse. So I've got to use another equation here to find the impulse, because we had a second equation we saw earlier. Impulse is also the change in momentum. That's the final momentum minus the initial momentum. So in order to find impulse, it's really the mass times final velocity minus the mass times the initial velocity. Plugging in our numbers here, I've got 0.1 kilograms times my final velocity of 0 meters per second. And I'm going to subtract from that 0.1 kilograms times the 20 meters per second I'm moving initially. When I plug that into my calculator, your impulse is going to end up being -2 kilogram meters per second. I can then use this up in my equation that I learned today. -2 kilogram meters per second is going to be force times my 1 second. Dividing by that 1 second, the force ends up being -2 newtons. Now here the negative is just telling you that the force is in a different direction than the velocity, which makes sense. For an egg that's, falling to the ground, the velocity is going down, but the force is clearly going up to stop my egg. And so that's where the negative comes from. Now what we've done here is use two different equations, and those two equations are important. They actually make up the impulse momentum theorem. What we can do is write one large equation that we're going to call the impulse momentum theorem. I know that J is Ft, I know that J is delta P. Combining those two, I could say that delta P, my change in momentum, equals the force times the time. Now plugging in for delta P, we know that delta P is really mvf minus mvi, right? So delta P is my final momentum minus the initial momentum, and that's going to equal the force times the time. This right here is my impulse momentum theorem, a very useful equation. Anytime you're dealing with an object that's changing its momentum due to a force or over a time, you can use the impulse momentum theorem to determine the unknown variable. I want to show you one neat thing about this equation that you're going to love. The neat thing here is if I divide by the time, I get mvf minus mvi divided by t equals f. If I factor out the m there, m vf minus vi divided by t equals f, I might recognize what this is inside the parentheses. Vf minus vi is the change in velocity divided by time. Change in velocity over time is acceleration. So I could substitute this right here as my acceleration, substitute in ma equals f. That looks like whose second law? Newton's second law. So the impulse momentum theorem is nothing more than another way of using Newton's second law. And in fact, this is actually how Newton really thought of his second law when he was back doing his physics, rather than what we use today as F equals ma. So it's a neat connection to what we've seen before. But regardless, now, go ahead and use the impulse momentum theorem like this. mvf minus mvi equals f delta t, or times t. Let's go ahead and see some examples of this here. Now, I'm going to do a lot of examples. What I'd suggest that you do is pause the video, give these examples a try yourself first, and then see if you can get the right answers as I go through them here. Let's take a look. Okay, so our first example. How long would it take to stop a 1,250 kilogram car moving 20 meters per second west if a force 8,450 newtons to the east was applied? Well, let's go ahead and list out our variables. We know the mass of my car is 2,250 kilograms. It's moving at a velocity of 20 meters per second west, and it's a force of 8,450 newtons to the east. So you notice they mention these directions. Direction is going to matter. These are vector quantities. In fact, momentum and impulse are both vectors. So we care about which direction these are going. So let's go ahead and say, when I did my practice here, I said that the east was positive. We're going to say that the east direction is going to be positive. Since my velocity is west, we can just say that that's negative 20 meters per second. My force then is going to be 8,450 newtons. And because it's moving to the east, it's positive. And then finally, I want to figure out the time here. Now this is my initial velocity. We're going to go ahead and stop it, so my final velocity is going to be 0 meters per second. Then we're going to go ahead and use the impulse momentum theorem. P final minus P initial equals F times T, or mvf minus mvi, just knowing the momentum is a mass times velocity. That's going to be my force times my time. Plugging in my numbers, 2,250 kilograms times my final velocity of 0 meters per second minus 2,250 kilograms times my initial velocity of negative 20 meters per second is going to equal the force, which we know to be 8,450 newtons, times the time. If you solve all that out in your calculator, this is going to end up being 0. You multiply those, divide by that. I get a time, it looks like, of 5.33 seconds. Okay, let's try example problem number 2. Very similar here. How long would it take to stop a 1,500 kilogram car? So my mass I know is going to be 1,500 kilograms. It said stop. That tells me my V final is 0 meters per second. It's moving at 15 meters per second west. Let's once again say that that is negative 15 because we're going to make the east direction positive, and it has a force of 6,500 newtons to the east, which means it is positive. We're going to go ahead and find the time using my same equation from before. mvf minus mvi equals F times t. Plugging in my numbers, m is going to be 1,500 kilograms. My final velocity is 0 meters per second, minus my 1,500 kilograms times negative 15 meters per second is going to equal 6,500 newtons times the time. Go ahead, this is going to be 0. Solving that out, 1,500 kilograms times the minus 15 meters per second divided by 6,500 newtons. I end up getting for my time 3.46 seconds. Okay, so this is how to find stopping time. You can use the impulse momentum to figure out how long it would take to stop a car if you apply a force, or anything really. Could be a truck, whatever you want it to be, with that there. Let's go ahead and try some different problems though. A different way you could ask a problem is to say if I have my car moving at 20 meters per second west and I apply a force to the west for 1.5 seconds, I want to now know what's the final speed of my car. Well, listing out my variables. My mass is 2,250 kilograms. It's now moving at 20 meters per second west. That's my VI. And the force is also to the west. So let's just go ahead and make west positive for both of these so all my numbers are positive. My force is 8,450 newtons west, and my time is 1.5 seconds. Now I want to solve for my final speed. I can use the same equation, set it up, mvf minus mvi equals F times t. Plugging in my numbers here, 2,250 kilograms, I don't know VF, minus, not equals, sorry, 2,250 kilograms times VI, which is 20 meters per second. That's going to have to equal my force times my time, which is 8,450 newtons times the time of 1.5 seconds. It looks like when I solve these in my calculator that this equation ends up being 2,250 kilograms times VF. I end up getting for this number here 45,000. For this number here, I get 12,675. When I add those together, I end up getting 57,625. Perfect. 2,675. And so when I solve that for VF, my final velocity ends up being 25.6 meters per second. Let's try our last one then. So my last one, very similar thing, but now I'm moving at 15 meters per second west, but my force is now to the east. Let's go ahead and still make west positive. But when I list out my variables now, mass of 1,500 kilograms, my VI is 15.0 meters per second. We're going to make that positive. My force is now going to be negative 6,500 newtons. Don't forget that direction matters because these are all vector quantities. And my time is now 2.5 seconds. I want to know the final speed of my car. So going here, mvf minus mvi equals F times t. Plugging in my numbers, 1,500 kilograms times VF minus my 1,500 kilograms times VI. My VI is 15.0 meters per second That's going to equal my force, negative 6,500 newtons, times the time of 2.5 seconds. If I go ahead and solve those numbers out, for this here I get negative 22,500. For this one here I get negative 16,250. And so when I go ahead and add that to the other side, I get that 1,500 kilograms times VF is going to equal, it looks like 6,250 dividing by the 1,500. VF ends up being 4.17 meters per second. Okay, so that's how to apply the impulse momentum theorem to a variety of problems. I hope you've enjoyed it. Thanks and have a great day.